Okay, students, here we go again. Let's see what we can do. Chapter 5. All right, I'm back in my classroom. Much better, too. Okay, looking at Newton's laws and at their applications and looking at equilibrium. All right, something you need to understand is that anytime an object is at rest, it is at a state of static equilibrium, okay? When it's not moving, it's static equilibrium, okay? So in other words, a book sitting on a counter, a picture hanging on a wall, a red light hanging from a cable, it's not moving, it's in static equilibrium. However, if an object is moving with, and here's the key, constant speed, then you have, and that's acceleration is equal, you have what is called dynamic equilibrium, okay? So how do we write this mathematically? Well, as you see, we say the sum of the forces is equal to the mass times acceleration, which is equal to 0, okay? It's very important to understand this concept because it makes the problems we solve much easier. Now, here's some tips of how to set up and to look at equilibrium problems. Of course, we're looking at Newton's second law. Always check to see that acceleration is equal to 0, okay? However, if it's not equal to 0, if it's accelerating, then you have to say this, F is equal to ma. You have to take that into consideration, okay? All right, now, okay, let's look at the orangutan here hanging from a cable. Let's look at the forces we have involved. Now, notice we have tensional forces. He's hanging from a rope or a vine. And then we have the force of weight. He is not moving. Okay, he's just hanging there. So he is at static equilibrium. And so therefore, we say what? Well, we say that the force is F is equal to ma, which is equal to 0 newtons. He's not moving. All right, so how would we find his weight? Well, you see your diagram here, T minus mg is equal to 0. He's not acceleration. So T is equal to mg, or his weight, so he would have a weight of 500 newtons, okay? The tension in the rope, I think it says what is the tension in the rope, excuse me. The tension in the rope would equal the weight, okay? Very simple, all right? What about a car? Now let's look at a car being towed. Now, here again, we want to draw our forces at work. We got our normal forces. We've got weight, got mg, and I always like to write it mg. I don't, we know that weight, it's weight, but I always like to write it as mg. Then we have frictional forces, okay? We have frictional forces, and the frictional force is 320 newtons, okay? So we draw our frictional force. That's frictional force right there. Okay, and it says, what is the tension in the rope? Okay, well, we don't know the car's acceleration. It's towed at a steady speed. Okay, so that means it's not accelerating. So we would write what? F is equal to ma. So it is not accelerating. F is equal to ma is equal to 0. It's steady speed, constant speed. So how do we find then the tension in the rope? Well, notice we have some components here. The sum of the forces in the x direction is equal to what? Well, it'd be T cosine of theta minus friction, right? Okay, and that's static friction or kinetic friction. It'd be kinetic, right? Yeah, kinetic, okay. All right, which is equal to 0. And so then we do what? We've got the y direction, but do we need to write the y forces? Because which way is the car moving? The car's not moving up and down. It's moving what? It is moving to the right? So if we want to find the tension then, that'd be what? The tension is equal to what? Well, we have to equal it to something, so T cosine theta it'd be equal to what? Friction over what? Cosine theta, right? And so what would the actual force be? And it's a 20-degree angle, so we get what? Frictional force is 320 divided by cosine of 20 degrees. And the tension in the rope is 340.1 newtons. Okay, I got to pause a minute. Okay, make sure my mic's working. Yeah. Okay. Didn't mean to do that. All right. So that's how we'd find that problem. Okay, or solve that problem. Again, we don't need the Y forces because it's not moving up and down. Okay. All right, dynamic laws, dynamics and Newton's second law. Of course, his second law, regardless of whether it's moving in the X and Y direction, remains the same. Notice it says the sum of the forces. All right, you already have, you already have that equation. You already have that equation on your worksheet, okay, on your formula sheet. All right, so if we look at a golf ball, all right, let's see. All right, we've got, want to know if the golf ball will make it to the hole. A putter puts a 46-gram golf ball with a speed of 3 meters per second. The friction exerts a 0.02 Newton retarding force on the ball, slowing it down. Will her putt reach the hole 10 meters away? Okay, well, the first thing we got to do is do what? Well, we draw all of our, why they drew it that way. They drew the acceleration to the left. I'm going to draw it to the right. So it's accelerating to the right, okay? And we want to know if it's going to go in the hole over here 10 meters away. Well, it has a speed and initial velocity of 3 meters per second, and the final velocity will be equal to 0 meters per second, because when it gets in the hole, it stops, right? Okay, now, so the frictional force, kinetic friction, is what? 0.02 newtons, right? That's kinetic frictional force. So what is the acceleration of the ball, right? Well, we know that the force and frictional forces are actually the same thing. A force is a force. So acceleration is equal to mu k over the mass, and so we got what? 0.02 newtons divided by the mass of the ball, which is 46 grams, and we got to put that in kilograms, so it's going to be 0.046 kilograms, right? And so we get an acceleration of what? So we got 0.02 divided by 0.046, and we get what? An acceleration of 0.43, we'll say 5, we'll round it up, meters per second squared. And you say, well, now wait a minute, why did you use the frictional force? Because that is the force which is the retardant force on the ball. Okay, that is what is, that's the force that's acting on it, that's slowing it down, that's going to stop it, okay? All right, so that's the acceleration of the ball. Now, what do we need to do? We need to find the, and I'm going to erase part of this, we need to find the distance and see if it's going to make it, right? Well, what do we have? Well, we have acceleration, and that was what? Let me write it down over here. The acceleration was 0.435 meters per second squared, okay? All right, now, we have acceleration, we have a final distance. The initial, then that's x final, by the way. X initial will be 0, okay? So we have this wonderful equation, v final squared is equal to v initial squared plus 2a delta x. And so we want to find what? Well, let's take delta x and let's break that apart into what? Let's break that apart this way. We're going to say x final minus x initial. All right, now we know that term right there is gone, okay? Because x initial starting point is 0. So we know the initial velocity is that. We know the final velocity is what? It's 0, isn't it? So that term is gone. You see what I'm doing here? All right, so let's start working this equation. Well, let's subtract a vi squared to both sides. So we got vi squared. Okay, and by the way, it's vi squared and then negative, okay? All right. You say, well, why is that? Well, you'll see here in just a minute, okay? And by the way, that acceleration, is negative. I almost forgot that. All right? And then we're going to divide by 2a, right? And it's going to be equal to what? X final, all right? Okay, so let's plug everything in. V initial square, and that's negative 3 meters per second squared, okay, over 2 times what? Negative 0.435. Okay, notice the negatives cancel out. So we got 3 squared, which is 9, and 9 divided by, 9 divided by 2. 2 times 0.435. Y'all, cannot keep from making a mistake. So 2 times 0.435. And we get an answer of the X final is 10.3 meters. Well, will she make the putt? Well, she has enough acceleration to make the putt, provided she aims properly, okay? So yes, she'll make the putt, all right, provided she aims properly, okay? Okay. All right, now what about mass and weight? All right, remember, mass and weight are not the same thing. Mass is actually the measure of an object's inertia to resist change in motion. Okay, so actually, and I know we always say, well, mass is the amount of matter in an object. Well, you're right, but it's actually we're actually measuring the tendency of an object's resist being changed in motion, or in other words, we're actually measuring its inertial force, okay, and the tendency of that to not change, okay. We're measuring its inertia. However, weight is a gravitational force, okay, and we've already covered this, and yes, it is negative technically speaking, but we can drop that negative off when needed, because typically that negative works out in the equations, as you've already seen. Now, so what about mass, the comparison of conversion between force units and mass units? Notice that 1 pound is equivalent to 4.45 newtons. However, 1 newton is 0.225 pounds, very, very small amount. When we look at kilograms to pounds, notice that 1 kilogram, and notice that 1 pound is that many kilograms, or 454 grams, okay? So if we were to look at what are the weight in newtons and mass in kilograms of a 90-pound gymnast, a 150-pound professor, and a 240-pound football player, what in the world would it look like? Well, here's what it would look like, okay? I didn't want to work all those out. I just went ahead and let the book show you, all right? Okay, that's how you would solve those problems. 90 pounds, we want to go to newtons, 150 pounds to newtons, 240 pounds to newtons, and then we want to go to kilograms. And there you go, okay? All right. Okay, that's the rest of that problem. All right, now what is apparent weight? There's a difference in weight and apparent weight. Apparent weight is basically the sensation of weight due to the forces that are acting on you, okay? And here they tell you the weight apparent is the magnitude of supporting contact forces. Well, all right, well, what about someone in an elevator? Well, your apparent weight is actually equal to the weight plus the mass times the acceleration. Now, why is that the case? Well, if you look at this, if you have an elevator, it's accelerating upwards, okay? So it's accelerating upwards, all right? And the weight, of course, is in the opposite direction. And then, of course, you have your normal force, and your normal force will actually equal the tensional force here on the elevator. Well, if you write this, you would write it, the sum of the forces is equal to T minus mg is equal to ma. Therefore, T is equal to what? Mg plus ma. And mg is weight. And you say, well, wait a minute. I want to know my apparent weight. Well, the tension would equal your apparent weight, okay? It would equal your apparent weight. All right, now, what about free fall and weightlessness? Just because we feel like we don't weigh anything does not mean we do not have weight, okay? An object that is weightless has no apparent weight, okay? And again, you say, well, how does that happen? Well, when a plane, if a plane, here you see them climbing at a very high rate of speed, they eventually come to a point to where they're weightless, or they feel like they're weightless, okay? Because, and again, they have to get pretty far away from the center of gravity too, away from the surface. But please don't misinterpret the what we mean by weightless and weight, okay? Doesn't mean you do not have weight. All right, normal forces. Normal forces, again, is an object that is a force in which it is perpendicular to the surface of contact, okay? And we've already talked about this. We look at the book here, we see that the book, the hand is on the book. Well, therefore, there's a normal force that is perpendicular to the surface right here, perpendicular to the surface, and that's our force normal, okay? And then, of course, weight is in the opposite direction of that. mg, or weight, is in the opposite direction of that. And how do we find the normal force? Well, the normal force typically is equal to the weight, okay, unless it's on an incline. And what about on an incline? What about acceleration of someone on an incline? How does that affect everything? Well, if you look at this, let's draw all of our vectors here. And they've drawn it, but I'm going to draw it a little differently. If you look at someone on an incline, let's just draw a box. Okay, we have the normal force in this direction. We have gravity in that direction. That's mg. Okay. Now, if the object is accelerating, guess what? It's moving that way, right? It's accelerating in that direction. So the sum of the forces is equal to ma, right? It's not equal. The sum of the forces is equal to ma, and it's accelerating. So we don't put 0. We put ma, right? Because it is accelerating. All right, so let's start drawing our vectors. Well, remember now, if the box is accelerating down the hill, well, looky here. That vector coincides with this vector, okay? And remember, whatever the angle of the hill is, okay, let me erase this. Whatever the angle of the hill is, okay, it's accelerating that way, all right, mg. And let's just say the angle is, I don't know, they're saying 27 degrees. Well, guess what? That angle right there is 27 degrees, okay? All right, now, and then we draw our corresponding vector. It corresponds with the acceleration, and we want to find what the acceleration is, right? Well, we know that F is equal to ma, right? So we know it's accelerating. But what about, remember, you got your normal force right here. So how do we find acceleration? Well, the normal force is equal, force normal minus, now look, is this cosine or sine? All right. Well, in actuality, this would be, this line right here would be mg cosine, because it's adjacent over hypotenuse theta, right? Okay. So the normal force would be what? Normal force would be equal to mg cosine of theta, right? But that's not what we're looking for. We're not looking for the normal force. We're looking for the acceleration. So the acceleration is right here. This is the vector that corresponds. Well, what is opposite over hypotenuse? Well, that's sine, right? So then this is what? Mg sine theta. So we have mg sine theta is equal to ma. Therefore, A is equal to what? G sine theta, isn't it? You say, well, wait a minute. Well, let me go ahead and write it. All right, so we got mg sine theta over m. But now, wait a minute. The mass is the same. So those cancel out, and it becomes g sine theta. And we've already actually done this. So I can actually find the acceleration going down a hill if I know my, and I mean just sliding down a hill, if I know my angle, I know G, 9.8, and so there you go. That's how you would find it. It's very, very easy. And I showed you how that works there using your free body diagram. Okay? All right, what about friction? We have, of course, static friction and kinetic friction. Remember, static friction is the sticky force, sticky friction. It keeps things from moving, okay? If we have a box in static equilibrium, then guess what? The static friction must balance the pushing force. That means it's not going anywhere. So the force applied is equal to or less than the static force, okay? Now, how do we write static friction, all right? Well, of course, eventually the woman keeps pushing, she's going to cause the box to move, right? All right, well, since we have, going back to this slide, looking at it, we have a normal force, right? That's force normal. And then we have mg, don't we? Yeah, we sure do. All right, now where's the frictional force? Well, if she's pushing that way, guess what? The frictional force is that way. So how do we find the frictional force? The frictional force then, here's another equation to add to your formula card. Force static max is equal to the coefficient of static friction times and remember that is the normal force. That right there is normal force, okay? All right. Now, one thing you need to understand about static friction. You know, for years it was thought that the static friction of an object could not be greater than 1. Well, that's not true. It has been discovered that there are materials out there that have a greater coefficient of static friction than 1. Some of them have a very high coefficient of static friction. You say, well, how does that work? Well, how do you think these dragsters work when there's a huge amount of force applied to those tires and they don't slip? They don't want them to slip, okay? And so, you know, it has to have a higher coefficient of static friction, higher than 1 anyway, okay? All right, now, box on a rough surface pulled by a horizontal rope with a tension T. The box is not moving. In this situation, it has to be what? Well, needless to say, it has to be equal to or less than, okay, because it's not moving, the tensional force, all right? Equal to or less than the static frictional force, all right? Okay. Now, what about coefficient of kinetic friction? Remember, we've already talked about this. This is when an object is in motion, it's moving, it's sliding. You know, when you're sliding the box, then guess what? But it's the same applies. Notice the only thing we do is change it to a K. Okay, change it to a K. And then we have rolling friction. Well, guess what? It's the same. You just change it to the coefficient for rolling friction, all right? Okay, and here's some coefficients. Rubber on concrete, steel on steel. All right, notice the difference in static, kinetic, and rolling. Wood on wood, wood on snow, ice on ice, and so on, okay? So notice that these numbers drop, okay, and they have to drop. The coefficient rolling have to be less than static because they're moving, okay? That's just common sense. All right. Again, here it shows you the formulas, and you do need to know these. You do need to put these on your formula card, okay? Here are some tips for working with kinetic friction. Notice kinetic is sliding, rolling is rolling. I think that's pretty obvious. And static means it's not moving, okay? All right. What about drag? Drag is pretty easy. Drag, of course, is similar to, it is a force of friction, okay? Except it's kind of like a fluid friction. It's air. It's air causing resistance, okay? And it could be water, though. It's not always air. It could be water. Could be a liquid, okay? Now, one thing about drag is that it increases in magnitude as the object speed increases. Well, that kind of goes without saying, does it not? Because if that wasn't the case, then why in the world does the space shuttle and these other spacecraft, when they re-enter the atmosphere, get so hot? Okay. If that wasn't the case, they wouldn't get hot, all right? But we know that's not the case. They do get hot, all right? So that proves that it increases in magnitude, okay? Of course, common sensical here that low speeds have low drag, high speeds have higher drags, no duh. Things that affect drag, of course, the diameter of the object, the size of the object. It's if the object speed is less than a few hundred meters per second and the object is moving through air near the air surface, okay? So, you know, those are things that we can use to model them. All right, how do we write, what is the equation for drag? Okay, in our everyday experience, the drag force can be written this way. And of course, the motion is opposite in direction. However, if we want to look at the density of air, okay, notice they talk about the the density of air is, you have to throw that in there. There's your density, okay. The A is the cross-sectional area of the object, and the drag coefficient CD depends on the details of the object shape, okay. However, the value for D for everyday moving objects is roughly half, so a good approximation of the drag force would be what? Right here. Here's your equation you want to use, okay? All right, so we can drop that off and just say 1/4, okay? All right, okay? So there's your equation for drag. Now, what do we mean by terminal speed? When an object is falling through air, it will eventually reach terminal speed. And a terminal speed basically is when there is no acceleration. Acceleration, when you reach terminal velocity, then acceleration is 0, okay? When you reach terminal velocity, it is 0, all right? So as an object is falling through air, when the drag force is equal to the weight of the object, right here, then you have no acceleration. All you have is what is called terminal velocity, okay? What about interacting objects? We look at interacting objects, we're looking at Newton's third law, which is the action-reaction law. An object will act on another object equal and opposite in direction. Now, for example, if we're looking at these two blocks here, when the hand pushes on A, you got to realize that the hand is pushing on A, and A is pushing back on the hand, and then A is pushing on B, and B is pushing back on A, okay? And if the hand has the net force, which in this case it would, then the object will accelerate. Now, notice right here what they tell you, that the acceleration of A is equal to the acceleration of B, which is equal to the acceleration of X, okay? And you say, well, how is that the case? Because they are touching, they are together, okay? Now, and notice it says we can't solve the motion of one block without considering the motion of the other block. So, here are some good little steps to go by for contact forces. Of course, you draw each one separate the force, draw a separate free body diagram for each object, write Newton's second law, of course, a component for each object, and then the two objects in contact exert forces on each other, okay? These are good rules to go by. Now, let's look at the situation here. Consider the situation and figure which pair of forces is an action-reaction pair. Well, is it the object being pulled with 20 newtons on B, or is it A on B, or is it B on A? Well, let's see. They tell us that the normal force on A due to B and the weight of A. Those are action-reaction pairs, okay? All right, now, let's look at this situation here. We got a hand, the hand force applied is, let me erase that. Force applied of the hand is 3 newtons, okay? 3 newtons, all right? And notice that block A has 5 kilogram mass and block B has a 10 kilogram mass, right? And so in front of this block is the two blocks move together. So that means what? F is equal to MA, isn't it? It's not equal to 0, the sum of the forces, right? And so we've got the force of the hand, okay, plus MA of A and MA of B, right, is equal to what? MA, right? The acceleration. All right, so how can we find then the force of, how can we find the acceleration? All right, well, remember what we said, the acceleration of all three of these are going to be the same. So what we can do then is just say that the acceleration is equal to the force of the hand over what? Mass of A plus mass of B, right? Because remember, the accelerations are all going to be the same. Okay, so we get what? We get the acceleration of A and B are equal to what? 3 newtons, right? Divided by, well, 5 and 10 is 15, right? 15 kilograms, all right? And so we get an answer of what? 3 divided by 15, I think it's 0.2. Yeah. So that's 0.2 meters per second squared. Okay, now, all right, now, look at what the question says. What force does A exert on block B? Okay. All right, well, we know that everything's moving with that acceleration, correct? Okay. But now let's look at each block individually, okay? Let's look at the net force for each block individually, all right? Well, A, the force on A is equal to what? Well, its acceleration, its mass is 5 kilograms, and its acceleration is 0.2 meters per second squared. So the force then is what? 1 Newton, right? 1 Newton. I think 5 times 0.2 is 1. Yeah, sure is. Sure is. It's 1. So that's 1 Newton, right? 1 Newton. Okay, so this one has a net force of 1 Newton. But now wait a minute. There is a 3 Newton force here. So at this point right here, what happens? Well, now listen, we're talking about block A. We're not talking about A and B. Block A has a mass of 5 kilograms and is accelerating at 0.2. So guess what? Equal and opposite. Now look. So what is the net force here? Well, this one has a force of 1 Newton in the opposite direction. So 3 minus 1 is equal to 2 Newtons, right? And so A then, what's remaining? We have 2 Newtons remaining. So A on B is a 2 Newton force, okay? And that's how we'd find that. All right, now. All right, we got boxes A and B are being pulled to the right on a frictionless surface. The boxes are speeding up. Box A has a larger mass than box B. How do the tension forces compare? Well, which one do you think is going to have the higher tension? Okay. Is T1 greater than T2? Well, let's see. T1 just has A hooked to it. Okay. B is actually the one pulling on T1. So is T1 going to be greater than T2? Because look, T2 is pulling both of them. Would they be equal? No. I think it would be this one, would it not? T1 has to be less than T2, and it most certainly does. Okay? Because it's pulling both of them. Whereas this one's just pulling A. T1's just pulling A. All right. All right. This is kind of a tricky question. People really stump their toe on this one. What will the pulleys read? They're both 5 kilograms, right? Will it read 10? Will it read 0? They're going to cancel each other out. No, they're not. It's going to read 5 kilograms. Okay? All right. Because the force of gravity pulling this one down and the force of gravity pulling this one down are the same. So it's going to have to actually it would read, well, according to what it is, it's kilogram scale, it'd read 5 kilograms. Okay. Ropes and pulleys. All right, now, what about a rope? We've actually already talked about some of this. Remember, if the object is not accelerating, the sum of the forces is equal to 0. However, if you have something hanging from a rope, then we know that what? Let's say, go to another. Let's say we got a rope and got a box here, okay? We have weight, mg, and then we have the tension of the rope that way, don't we? Well, all right, it's not accelerating, so the sum of the forces is equal to 0, okay, is equal to ma, which is equal to 0. So, what do we have then? We have T minus mg is equal to 0, so T is equal to mg. And that's how we would find it, okay? Now, what if it's accelerating? Well, we'd have to throw acceleration in there as to whether it's going up or going down. If it's going up, it'd be positive acceleration. If it's going down, it'd be negative acceleration, okay? All right. And that's how we would find the tension, all right? So if it was accelerating, it would look like this. T minus mg is equal to ma, and so T, and if it was going up, all right, and so T would be equal to what? Mg plus ma. What if it was going down? Well, it would be T is equal to mg minus ma. Okay, the tension would be less. if it was like an elevator, okay? All right, notice they tell you generally the tension in a massless string or rope equals the magnitude of the force pulling on the end of the string or rope. What I just told you, okay? What I just told you. All three 50-kilogram blocks are at rest. The tension in rope 2 is what? It has to be equal to 1, y'all. Come on. It has to be. All right? They're balanced. They're not moving, okay? And that's it. And I hope that this lecture will help.